The universe was supposed to cooperate. When the James Webb Space Telescope opened its eyes in the summer of 2022, it was meant to be the crowning achievement of an era scientists had already named. They called it precision cosmology. The big picture was settled. The numbers were known. The story of how the universe formed, grew, and became everything we see today had been told with breathtaking mathematical precision. All that remained was to confirm the final details. To watch the early cosmos assembling itself in real time, exactly as predicted. Instead, within weeks of receiving its first data, astronomers around the world found themselves staring at something the models had never anticipated. Scattered across nearly every deep field image the telescope captured were tiny, intensely red points of light. Compact, brilliant, everywhere. They appeared in scenes from the cosmos as it existed within the first 2 billion years after the Big Bang, and then they vanished just as abruptly as they had appeared. Nobody knew what they were, and the attempt to find out cracked open a set of problems that nobody has yet been able to close. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing, because what you're about to see only gets more surprising from here. And I post videos like this every single day. Now, let's continue. 13.8 billion years ago, space itself began to expand from a state of extreme density and temperature. Not an explosion in space, but an expansion of space. In the first fractions of a second, the universe inflated faster than the speed of light. Within minutes, the earliest atomic nuclei formed: hydrogen, helium, and trace amounts of lithium. For the next 380,000 years, the cosmos was an opaque, glowing plasma. Photons could not travel more than a short distance before bouncing off free electrons. Light was trapped inside the fog. Then the universe cooled to roughly 3,000 degrees. Electrons slowed enough to bind to protons, forming neutral hydrogen atoms for the first time. The fog cleared. Light streamed outward in every direction. That light has been traveling ever since, stretched by billions of years of cosmic expansion from its original visible wavelengths into the microwave range. We call it the cosmic microwave background. It is the oldest light in the universe, and it is one of the most precisely measured things in all of science. After that moment of first transparency came the cosmic dark ages. No stars, no galaxies, just vast cool clouds of hydrogen and helium drifting through an expanding void. Over hundreds of millions of years, gravity slowly gathered those clouds. Dense regions attracted more gas. Temperatures inside them rose. And eventually, scattered across the void, the first stars ignited. Massive, short-lived. They burned through their fuel, scattered the first heavy elements into the surrounding gas, and died. Those elements became the building blocks for the next generation of stars, which formed inside the first primitive galaxies. From that point, the standard model predicted a slow, methodical, bottom-up process of construction. Small galaxies formed first, then merged into larger ones. Dark matter, the invisible gravitational scaffolding making up roughly 27% of the universe's total energy budget, provided the framework. Gas fell into dark matter halos, compressed, and became stars. The halos grew by merging with one another. Over billions of years, that hierarchical assembly produced the grand spirals and giant ellipticals we observe in the modern universe. The key word in the whole story was slowly, gradual, from simple to complex, across immense stretches of time. This model, called lambda CDM, was not a rough guess. It was arguably the most successful mathematical framework in the history of science. Lambda stands for the cosmological constant, the mathematical term representing dark energy, the force driving the universe's accelerating expansion. CDM stands for cold dark matter. Together, they described a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. And for decades, every major observation confirmed it with remarkable precision. The cosmic microwave background showed tiny temperature fluctuations, hot spots and cold spots differing by millionths of a degree. Lambda CDM predicted the precise statistical pattern of those fluctuations before the most detailed measurements were made. When the European Space Agency's Planck satellite mapped the microwave background with unprecedented accuracy, the match was extraordinary. The model predicted where the peaks and troughs should appear, their heights, their spacings, and it was correct, point after point, to extraordinary precision. Surveys of millions of galaxies revealed a vast network of filaments and voids that supercomputer simulations running the lambda CDM equations had predicted years before the surveys were completed. The model worked on every scale, from the clustering of galaxy clusters down to the statistical distribution of galaxies across the sky. Scientists called it an era of precision cosmology. The James Webb Space Telescope was supposed to be its capstone, designed specifically to look back to the very first galaxies and watch them forming, catching the early universe in the act of building itself from scratch. It was supposed to show us the messy, gradual, small-scale beginnings that every simulation predicted. Instead, it found the finished product already there. The tiny red points of light scattered through its first images were the opening salvo of a much larger problem. Astronomers gave them a nickname: Little Red Dots. The name was informal, almost playful, the kind of shorthand researchers use before they understand what they are dealing with. The playfulness did not last. As observations accumulated and data piled up, the little red dots refused to fit into any existing category. By 2025, 341 of them had been catalogued, and nobody could agree on what they were. The initial theories were reasonable. Perhaps they were compact galaxies brightened by swarms of newborn stars. Perhaps they were active galactic nuclei, the blazing hearts of young galaxies powered by supermassive black holes consuming gas and dust at ferocious rates. Both explanations had serious problems. If they were star-forming galaxies, they appeared far too massive and too mature for the era they inhabited. The universe had not existed long enough to build what these objects seemed to be. And if they were black hole-powered engines, they were missing the signatures that every known active galactic nucleus displays. No X-rays, no radio waves. Those calling cards of feeding black holes were simply absent. The little red dots looked too massive to be ordinary star-forming galaxies and too quiet to be active black holes. They were something else. Then in January of 2026, a study published in the journal Nature by Darach Watson and colleagues at the University of Copenhagen's Cosmic Dawn Center cracked the mystery open. The team had obtained the highest quality spectra ever recorded for a dozen little red dots using the telescope's near-infrared spectrograph. When they analyzed the light from these objects in unprecedented detail, they found something unexpected. The spectral lines were broadened, but not by velocity, not by the Doppler effect of gas whipping around a black hole at tremendous speed, which is what astronomers would normally expect. The broadening was caused instead by electron scattering. Light was being scattered by an extraordinarily dense cocoon of ionized gas surrounding each object. What that meant was transformative. The little red dots were indeed supermassive black holes, but young ones, and far less massive than anyone had previously estimated. Earlier calculations, based on the assumption that the spectral broadening was caused by velocity, had placed these black holes at roughly 1 billion times the mass of our Sun. The new analysis revealed their true masses were 100 times lower, somewhere between 100,000 and 10 million times the mass of our Sun. Still enormous by everyday standards, but radically smaller than initial estimates had suggested. The cocoon of dense ionized gas surrounding each black hole was the key to everything. It was this cocoon that gave the little red dots their distinctive red color. The black hole at the center was consuming gas, generating enormous heat. That heat radiated outward through the cocoon, and the cocoon filtered and reddened the light. Rohan Naidu, an astrophysicist at the Massachusetts Institute of Technology, began calling these objects black hole stars. He and his colleague, Anna Christina Eiler at the Harvard-Smithsonian Center for Astrophysics, proposed that they were gigantic luminous balls of gas powered not by nuclear fusion, the way normal stars operate, but by a supermassive black hole sitting at their center, radiating energy through the surrounding cocoon. Not quite a star and not quite a black hole, but something of both. A new class of cosmic object, something no theoretical model had ever predicted. I think this is definitely by far the most exciting thing to come out of the James Webb Space Telescope, Naidu said. If you start thinking about them as essentially enormous stars with a black hole at their centers, things start falling into place. The missing X-rays, the absent radio emission, the strange spectral features, all of it makes sense if you stop trying to force these objects into existing categories and accept that they are something genuinely new. A separate study published in February of 2026 by Fabio Piccucci at the Harvard-Smithsonian Center for Astrophysics reinforced this picture from a completely different angle. Piccucci's team used radiation hydrodynamic simulations to show that the little red dots are best explained as direct collapse black holes. These are objects that form when a massive gas cloud in the early universe bypasses the star formation stage entirely and collapses directly into a black hole. The simulations reproduce the specific characteristics of the little red dots: their weak X-ray emission, the presence of certain metal lines, the absence of star formation features, their abundance, their compact nature, and their evolution over cosmic time. All their puzzling properties were explained within a single self-consistent framework without requiring any additional assumptions, whether they are best described as black hole stars or direct collapse black holes. The conclusion is the same. The early universe was building supermassive black holes faster and more efficiently than anyone imagined, and it was doing it through mechanisms our models had never accounted for. But the little red dots were only the opening problem. Before astronomers had even begun to understand them, the very first images the telescope returned had already sent tremors through the physics community, because scattered across those images were galaxies that had no right to exist. On July 12, 2022, NASA released the first deep-field image captured by the James Webb Space Telescope. The image showed a tiny patch of sky, a region no larger than a grain of sand held at arm's length. But within that grain of sand were thousands of galaxies, clusters of galaxies, arcs of light bent by gravity into shimmering streaks, a window into the deep past of the cosmos reaching back over 13 billion years. Scientists had expected to see the equivalent of a construction site. The early universe was supposed to be messy, chaotic, half-built. Infant galaxies should have appeared as dim, irregular clumps of gas and young stars struggling to take shape. Instead, what the telescope revealed was something that looked like the finished product. Enormous, structured, bright galaxies. Galaxies with spiral arms, galaxies with orderly disks. Galaxies that by every measure appeared mature and fully formed. Except they were not ancient, they were impossibly young. They existed when the universe was only a few 100 million years old. Imagine pressing play on a time-lapse of a skyscraper being built. You expect to see the foundation laid, the steel frame rising floor by floor, the slow and deliberate process of construction. Instead, the very first frame of the video shows the 50th floor already complete. The crane is already on the roof. The lights are already on. In January of 2026, the situation escalated further. A team led by Rohan Naidu at the Massachusetts Institute of Technology confirmed the most distant galaxy ever observed. Its designation is MOMS 14. The name comes from the survey that found it, the Mirage survey, designed specifically to test whether these absurdly distant bright galaxies are real or observational artifacts. MOMS 14 is real. Its redshift was confirmed at 14.44, meaning its light has been traveling through expanding space for about 13.5 billion years. We are seeing it as it appeared just 280 million years after the Big Bang. That number deserves a pause. 280 million years. In cosmic terms, that is nothing. The universe was an infant, and yet MOMS 14 is bright, compact, and chemically enriched. It contains nitrogen in quantities that should not be possible so soon after the beginning. Nitrogen is produced inside massive stars and released when those stars end their lives. For nitrogen to appear at these levels, multiple generations of stars had to have formed, burned through their fuel, and scattered their processed elements into the surrounding gas, all within 280 million years. The standard model said this could not happen that fast. Even more remarkably, MOMS 14 appears to have cleared its immediate surroundings of primordial hydrogen gas. The early universe was filled with a thick fog of neutral hydrogen, the remnant of the initial conditions after the Big Bang. For the fog to clear around a galaxy, that galaxy must produce enough ultraviolet radiation to ionize the hydrogen, breaking it apart atom by atom. This process, called reionization, was supposed to happen gradually over hundreds of millions of years. MOMS 14 seems to have accomplished it in its own neighborhood, at a point in time when virtually every model predicted the universe should be completely neutral. And MOMS 14 is not an outlier. The survey that discovered it found that bright galaxies at these extreme distances are roughly 100 times more abundant than pre-launch predictions suggested. Not 10% more, not double, 100 times more. There is a growing chasm between theory and observation related to the early universe, one researcher noted, which presents compelling questions to be explored going forward. But the impossible galaxies are not limited to the most distant ones. At somewhat closer distances, Still deep in the early universe, the telescope found something arguably even more disturbing: dead galaxies. Galaxies that had already stopped forming stars entirely. One of the most striking examples is a galaxy called GS9209. This galaxy formed the vast majority of its stars within the first 800 million years after the Big Bang. It built itself rapidly and aggressively, consuming gas and igniting stars at a furious rate. And then it stopped completely. By the time the universe was 1.8 billion years old, GS9209 had already gone quiet. Its star formation had ceased. It had lived its entire productive life and shut down before most galaxies in the universe had even truly started. Picture a neighborhood where homes are being built. Foundations are being poured. Frames are going up. It will take years before anyone moves in. And in the middle of this construction zone sits one house that is not only finished, but abandoned. The owner moved in, lived a full life, and the house stands empty. All before the neighbors finished laying their foundations. That is GS9209. It lived and died in an era when the universe itself was barely getting started. The total stellar mass observed at high redshift, the combined mass of stars in galaxies seen in the early universe, appears roughly 10 times higher than what computer simulations produce when they model galaxy formation using the standard rules. 10 times is not a rounding error. It is not a calibration issue that can be resolved by tweaking a few parameters. It is a structural problem. The simulations are built on the most successful model in the history of cosmology. They incorporate everything we think we know about gravity, dark matter, dark energy, and the physics of gas and stars, and they are producing answers that are wrong by an order of magnitude. To understand how serious this is, you need to understand the model they are contradicting. Lambda CDM builds structure from the bottom up. Dark matter halos form first. In the early universe, slight fluctuations in the density of dark matter, seeded by quantum variations in the first moments after the Big Bang, grew under gravity into increasingly dense clumps. These clumps attracted ordinary gas. The gas fell into the gravitational wells, compressed, cooled, and eventually ignited into stars. The first galaxies formed inside dark matter halos. The halo was the foundation. The galaxy was the building constructed on top of it. Halos grew by merging. Small halos combined into larger ones. Over billions of years, this hierarchical process built everything from dwarf galaxies to the massive clusters containing thousands of galaxies. This bottom-up model is one of the great achievements of Lambda CDM, and the James Webb Space Telescope is breaking it. The galaxies the telescope is finding in the early universe are too massive for the halos that should have been available at that time. The halos grow through a process that takes time. Dark matter particles interact gravitationally but slowly at cosmic scales. Small halos must form first, then merge again, building up to sizes capable of hosting large galaxies. The timeline is set by the physics of gravitational collapse. It cannot be rushed, but the telescope is finding galaxies that look as if they were built on foundations that should not have been ready. This presents three uncomfortable possibilities. The first is that dark matter halos formed more efficiently in the early universe than our simulations predict. Perhaps there are physical processes we have not accounted for that accelerated halo growth. The basic framework survives, but our simulations need substantial adjustment. The second possibility is that dark matter behaved differently at the extreme temperatures and densities of the early universe. Perhaps its properties changed. Perhaps it interacted with itself, or with ordinary matter in ways it no longer does. The third possibility is the most radical. Dark matter may not be what we think it is. It may not be a particle. It may not be a substance. It may be a modification of gravity itself, an alteration in the way gravity works at very large scales or very low accelerations. This idea, once considered fringe, has gained traction since the James Webb Space Telescope began delivering its data. While the telescope was dismantling assumptions about galaxy formation and dark matter, a completely separate crisis was deepening around a single number. A number so fundamental that getting it right sets the scale for everything we know about the cosmos. In 1929, Edwin Hubble sat in his office at the Mount Wilson Observatory in California and looked at data that would change humanity's understanding of its place in the cosmos forever. He had been measuring distant galaxies, specifically how far away they were and how fast they were moving. Every galaxy he observed was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding. Not the galaxies themselves flying through space, but space itself stretching, the fabric of the cosmos growing, carrying the galaxies along with it. Hubble quantified this expansion with a single number, the rate at which the universe is growing. This number became known as the Hubble constant. It is measured in kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. The Hubble constant tells you that for every megaparsec of distance, galaxies are receding by a certain number of kilometers per second. Get this number right, and you can calculate the age of the universe, the size of the observable universe, the total energy budget of the cosmos, and the ultimate fate of everything in it. Get it wrong, and all of those calculations shift. For decades, measuring the Hubble constant was one of the central projects of observational cosmology, and for decades, the measurements were not precise enough to cause alarm. Different methods gave slightly different answers, but the error bars were large enough to overlap. Everyone assumed the discrepancies would shrink as instruments improved. Then the instruments improved, and the discrepancies did not shrink. They sharpened. They solidified. They became a crisis. There are two fundamentally different ways to measure the Hubble constant. The first method looks at the nearby universe. Astronomers identify objects whose intrinsic brightness is known. Certain types of pulsating stars called Cepheid variables, the tip of the red giant branch, a specific stage in stellar evolution, and type Ia supernovae, exploding stars with a characteristic luminosity. By comparing how bright these objects appear to how bright they actually are, astronomers calculate their distances. Combine those distances with measurements of how fast the galaxies hosting these objects are receding, and you get the Hubble constant. This method, called the distance ladder, gives a value of approximately 73 kilometers per second per megaparsec. The team that has pushed this measurement to its highest precision is the JWST collaboration, led by Nobel laureate Adam Rees, using data from both the Hubble Space Telescope and the James Webb Space Telescope. They have confirmed this value with extraordinary statistical confidence. The second method looks at the oldest light in existence. The Planck satellite performed a detailed measurement of the cosmic microwave background and extracted from it a precise picture of the universe when it was only 380,000 years old. Using the lambda CDM model, cosmologists project forward from those initial conditions across 13.8 billion years of cosmic evolution to predict what the expansion rate should be today. The value this method gives is approximately 67.4 kilometers per second per megaparsec, 73 versus 67.4. The gap is roughly 9%. In everyday life, 9% is nothing. In fundamental physics, 9% is a chasm. These are two of the most carefully conducted measurements in the history of science. They have been checked, rechecked, scrutinized for errors, repeated with different instruments, and subjected to every form of analysis the scientific community can devise, and they refuse to agree. This disagreement is called the Hubble Tension. In 2025, Duke University astrophysicist Dan Skolnick declared that the Hubble Tension had become a Hubble crisis. The James Webb Space Telescope was supposed to help resolve this. In 2024 and 2025, the SH0ES team used the telescope's superior resolution to observe the same Cepheid variable stars that the Hubble Space Telescope had previously measured. The concern had always been that Hubble's older instruments might be blurring the starlight, introducing errors through a phenomenon called crowding, where nearby stars blend together and make individual measurements less reliable. The James Webb Space Telescope's sharper vision would either confirm or correct the Cepheid measurements. It confirmed them. The local value of the Hubble constant held firm at approximately 73. The crowding concern was ruled out at high statistical confidence. Then, in May of 2025, Wendy Friedman's Chicago Carnegie Hubble program published results using a different technique. Instead of Cepheid variables, her team used the tip of the red giant branch method. Their result came in at approximately 70.4, with error bars wide enough to overlap with both the SH0ES value and the Planck value. Critics noted that this meant the measurement was consistent with everything, and therefore resolved nothing. The community erupted. Then, in December of 2025, a completely independent measurement arrived. The TD Cosmo collaboration used a technique called time delay cosmography. When light from a distant quasar passes near a massive galaxy, gravity bends it, creating multiple images of the same quasar. Because each image's light travels a slightly different path, the images flicker at slightly different times. By measuring these time delays with exquisite precision, astronomers can calculate the expansion rate without relying on any of the traditional methods. The TD Cosmo result, based on 8 gravitational lens systems, came in at approximately 71.6 kilometers per second per megaparsec, closer to the local measurements than to the cosmic microwave background value. The statistical significance of the overall disagreement between the two approaches has reached 5 sigma, the gold standard threshold in physics. The probability of this discrepancy being a random fluke is roughly 1 in 3.5 million. If both measurements are correct, and the evidence increasingly suggests they are, then either our model of the early universe is wrong, or our understanding of how the universe evolved from then to now is incomplete. There is no comfortable middle ground. Some theorists have proposed early dark energy, a brief burst of extra dark energy in the infant universe that would have altered the expansion rate before the cosmic microwave background formed. Others point to new neutrino physics or exotic dark sector interactions. Whatever the answer turns out to be, one thing is clear. The most precisely measured number in cosmology is giving 2 incompatible answers. And that measurement problem is intertwined with questions about the invisible scaffolding holding everything together. There is something holding the universe together that we cannot see. We cannot touch it. We cannot photograph it. No instrument has ever detected a single particle of it directly. And yet without it, nothing we observe makes sense. Not the rotation of galaxies, not the bending of light around massive objects, not the web of cosmic structure stretching across billions of light years. We call it dark matter. The name is misleading. It is not dark in the way a shadow is dark. It does not absorb or block light. It is dark because it does not interact with light at all. It passes through ordinary matter as if it were not there. It produces no electromagnetic radiation of any kind, no radio waves, no infrared, no visible light, no X-rays, no gamma rays. It is utterly transparent to every form of detection we have ever devised. And yet it accounts for roughly 27% of the total energy content of the universe, more than 5 times the amount of ordinary matter. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. The first clue arrived in the 1930s when astronomer Fritz Zwicky measured the velocities of galaxies within the Coma cluster. The galaxies were moving too fast. Based on the visible mass in the cluster, they should have drifted apart long ago. Something unseen was holding them together. The evidence sharpened dramatically in the 1970s when Vera Rubin and Kent Ford measured the rotation speeds of stars in spiral galaxies. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center. This made no sense if the visible stars and gas were the only source of gravity. In any system governed by Newtonian physics, objects farther from the center of mass should orbit more slowly. The outermost planets in our solar system move more slowly than the inner ones. Mercury orbits the Sun faster than Neptune does. But in galaxy after galaxy, Rubin and Ford found flat rotation curves. The outer stars refused to slow down. The only explanation that fit was a massive halo of invisible matter surrounding each galaxy, extending far beyond the visible disk and providing additional gravitational pull. Then came gravitational lensing. Einstein's general theory of relativity predicts that massive objects warp the fabric of space-time, bending the paths of light passing near them. Astronomers observed that light from distant galaxies was being bent around galaxy clusters in ways that required far more mass than visible matter could account for. Mapping the distortions allowed astronomers to map the distribution of dark matter, creating images of something invisible by observing its effect on light. So dark matter exists. The evidence is as strong as the evidence for many things we consider established facts of physics. But what it is remains one of the deepest unsolved questions in science. Despite decades of experiments using underground detectors shielded from cosmic rays, particle accelerators smashing protons together at nearly the speed of light, and satellite observatories scanning the sky for signs of dark matter annihilation, not a single dark matter particle has been directly detected. We know it is there. We do not know what it is. And the James Webb Space Telescope's early galaxy findings are breaking the standard picture of how dark matter does its work. Hidden in the oldest light in existence, older than any of these galaxies, older than the dark matter halos themselves, are anomalies that have been quietly accumulating for over 2 decades. anomalies that the James Webb Space Telescope is making increasingly difficult to dismiss. 380,000 years after the Big Bang, the universe did something extraordinary. It became transparent. Before that moment, the cosmos was a seething plasma so dense that photons could not travel more than a short distance before colliding with a charged particle and bouncing off in a random direction. The universe glowed, but was opaque. Then the temperature dropped below roughly 3,000 degrees. Electrons slowed enough to be captured by protons, forming neutral hydrogen atoms, and the photons that had been trapped inside the plasma were suddenly free. They streamed outward in every direction, and they have been traveling ever since. That light is still here. It fills the universe. It comes from every direction in the sky. In 1965, Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey accidentally detected it while calibrating a radio antenna. They could not eliminate a persistent background hiss coming from every direction. They cleaned pigeon droppings off the antenna. They checked every cable and connection. The hiss remained. It was the echo of creation itself. They received the Nobel Prize. The cosmic microwave background is almost perfectly uniform. Its temperature across the entire sky is 2.725 Kelvin, just a few degrees above absolute zero. But embedded in that uniformity are tiny variations, temperature fluctuations of roughly 1 part in 100,000, hot spots and cold spots differing by millionths of a degree. These fluctuations are the seeds of everything, the slightly denser regions in the infant universe that would eventually, over billions of years, gravitationally attract enough matter to become galaxy clusters, the slightly less dense regions that would become the vast cosmic voids. Every structure in the observable universe traces its origin to these microscopic temperature differences in the oldest light. But the cosmic microwave background is not entirely clean. Hidden within its near-perfect patterns are anomalies that have puzzled cosmologists for over 2 decades. Anomalies that were noticed, flagged, debated, and in many cases set aside as probable statistical flukes. The first is the cold spot, a region in the constellation Eridanus where the cosmic microwave background temperature is significantly lower than the surrounding sky. The cold spot is not just slightly cooler, it is cooler in a way that is statistically unexpected given the predictions of lambda CDM. It is too cold, too large, and too well defined. Multiple explanations have been proposed. A supervoid, an unusually empty region of space along the line of sight. A topological defect from a cosmic phase transition. Statistical noise. None has been universally accepted. The second anomaly is more unsettling. It is called the axis of evil, a name given half in jest by the cosmologists who first noticed it. When the large-scale temperature patterns in the cosmic microwave background are analyzed, they show an unexpected alignment. The largest fluctuations are not randomly oriented as a universe born from a uniform expansion should produce. They are aligned along a preferred direction in the sky. A universe that began as a random quantum fluctuation, inflating outward in all directions, should have no preferred direction. The isotropy principle, the assumption that the universe looks the same in every direction at large scales, is one of the foundational pillars of cosmology. The axis of evil challenges it. For years, these anomalies were treated as curiosities, interesting but not alarming. Then the James Webb Space Telescope began mapping galaxies at unprecedented distances. When researchers overlaid the telescope's galaxy maps onto the cosmic microwave background anomalies, something uncomfortable emerged. The distribution of early galaxies showed correlations with the anomalous regions. The pattern of galaxy clustering at high redshift appeared connected to the patterns in the oldest light. Not perfectly, not conclusively, but suggestively. Perhaps the seeds of galaxy formation were not as random as assumed. Perhaps conditions during or before the moment of recombination were more complex than the standard model accounts for. Perhaps exotic energy forms influenced the primordial plasma. Perhaps the initial conditions of the Big Bang itself were not the simple uniform inflation that lambda CDM assumes. When you zoom out far enough, when you step back and look at the universe at the very largest scales, the anomalies in the oldest light connect to something visible, a structure so vast it stretches across billions of light years. A structure that according to our best models should not exist. The universe has architecture. Galaxies are not evenly distributed through space. They are strung along enormous filaments, threads of dark matter and gas stretching hundreds of millions of light years in length. Where filaments intersect, galaxy clusters form, dense knots of thousands of galaxies bound together by gravity. Between the filaments lie voids, enormous empty regions where almost nothing exists. Some of these voids are hundreds of millions of light-years across. Together, the filaments, clusters, and voids form what cosmologists call the cosmic web. It is one of the most beautiful structures in nature, and it was considered one of the great triumphs of lambda CDM. But even here, at the larger scales, the telescope is finding discrepancies. It has discovered protoclusters, the precursors of galaxy clusters, at much earlier times than models predict. These protoclusters are further along in their development than they should be. They contain more galaxies, more organized structure, more gravitational binding than the standard simulations produce for those epochs. And the cosmic web has an even bigger problem at the very largest scale. The cosmological principle, the assumption that the universe is homogeneous and isotropic at sufficiently large scales, places a theoretical limit on how large a gravitationally bound structure can be. Based on the age of the universe and the speed at which gravity can pull matter together, the largest coherent structure should be no more than roughly 1.2 billion light-years across. Anything larger would require more time to form than the universe has existed. And yet astronomers have found structures that dwarf this limit. The Hercules Corona Borealis Great Wall, identified through the distribution of gamma-ray bursts, appears to be roughly 10 billion light-years across. The giant arc, discovered in 2021 through the analysis of quasar absorption systems, spans approximately 3.3 billion light-years. The Sloan Great Wall stretches over 1.3 billion light-years. Each of these exceeds the theoretical ceiling. If the cosmological principle is even slightly wrong, the consequences cascade through everything. The age of the universe is calculated assuming homogeneity. The expansion rate is measured assuming isotropy. The dark energy measurements depend on the assumption that space looks the same in every direction. Most researchers still believe the cosmological principle holds to a sufficient approximation. The anomalies may have conventional explanations. The structures may be statistical flukes, but the list of things that require conventional explanations is growing, and each new item adds weight to the alternative possibility that something fundamental about the model is incomplete. And now we come to the force that drives it all. The force that makes up 68% of everything in the universe. The force we named, but never understood. In 1998, two teams of astronomers made the same discovery independently. They were measuring the distances to Type Ia supernovae, exploding stars all of which reach roughly the same peak brightness, which means you can calculate how far away they are by measuring how dim they appear. The teams expected to find that the expansion of the universe was slowing down. Gravity should be pulling everything back together. The rate of expansion should be decelerating. Instead, they found the opposite. The expansion was accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been. The universe was not just expanding, it was expanding faster and faster. Something was pushing it apart. That something was given the name dark energy. It was not a discovery in the traditional sense. Nobody found a particle. Nobody detected a force. What the astronomers found was an absence. A gap between what gravity predicted and what the universe was doing. Dark energy is the name we gave to whatever fills that gap. The simplest description of dark energy is the cosmological constant, a fixed energy density built into the fabric of space-time itself. Every cubic meter of space, no matter where it is or what it contains, has the same tiny amount of energy. As space expands, new space is created, and the total amount of dark energy increases. This constant pressure drives the acceleration. The cosmological constant has a devastating theoretical problem. When physicists try to calculate the energy of empty space using quantum mechanics, they get a number that is catastrophically wrong. Not slightly wrong, not wrong by a factor of 10 or 100, wrong by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in the history of science. Quantum mechanics predicts that empty space should be seething with so much energy that the universe would have torn itself apart in the first fraction of a second after the Big Bang. Obviously, it did not. Something is cancelling almost all of that energy, but not quite all of it. A tiny residue remains. Nobody knows why. Nobody has a satisfying explanation for why the cosmological constant has the value it does. It is one of the deepest unsolved problems in fundamental physics. But for decades, The working assumption has been that whatever dark energy is, it is constant. It does not change over time. It does not evolve. That assumption may now be wrong. In March of 2025, the Dark Energy Spectroscopic Instrument, known as DESI, released the results of its second major data analysis. DESI is a remarkable machine mounted on the Nicholas U. Mayle 4-meter telescope at Kitt Peak National Observatory in Arizona. It can capture the spectra of 5,000 celestial objects simultaneously using a robotic array of fiber optic cables. Over its first 3 years of operation, it has mapped the three-dimensional positions of nearly 15 million galaxies and quasars, constructing the largest three-dimensional map of the universe ever made. DESI measures the expansion history of the universe by tracking a phenomenon called baryon acoustic oscillations. In the early universe, sound waves traveling through the primordial plasma left an imprint on the distribution of matter, a characteristic spacing like the rings left by a pebble dropped in a pond. That spacing serves as a standard ruler. By measuring the apparent size of this ruler at different distances, which correspond to different epochs in cosmic history, astronomers can track how the expansion rate has changed over the past 11 billion years. When the DESI team combined their measurements with data from the cosmic microwave background, supernova observations, and weak gravitational lensing surveys, the results were striking. The standard lambda CDM model, in which dark energy is a fixed cosmological constant, struggled to fit all the data sets simultaneously. The data preferred a model in which dark energy is not constant, a model in which the influence of dark energy has been weakening over time. The statistical significance of this preference ranged from 2.8 sigma to 4.2 sigma, depending on which combination of datasets was used. 4.2 sigma means the probability of the result being a statistical fluke is roughly 1 in 40,000. That is not yet the 5 sigma gold standard that physics requires to claim a discovery, but it is mounting, and it is getting stronger with each new data release. If dark energy is not constant, it has a different name in theoretical physics: quintessence, a dynamic field that evolves over cosmic time, sometimes stronger, sometimes weaker, its behavior governed by physics we have not yet identified. Quintessence models have existed in theoretical physics for decades, but they were always the less favored option. The cosmological constant was simpler, and in science, simpler usually wins until the data force you somewhere more complicated. The implications of evolving dark energy are profound. If dark energy has been weakening, the universe's past looks different than lambda CDM predicts. The rate at which structure formed, the timing of galaxy assembly, the relationship between the early universe and the present, all of these shift, and the universe's future changes too. Under a constant cosmological constant, the universe expands forever, accelerating until every galaxy beyond our local group recedes past the cosmic horizon and the sky goes dark. Under evolving dark energy, other fates are possible. If dark energy continues to weaken, the acceleration may slow. If it reverses sign, the universe could begin to contract. The end of the cosmos is not yet written. If dark energy can change, perhaps other things we assumed were fixed are not fixed either. Perhaps the very constants of physics, the numbers that govern how atoms behave, how light travels, how forces interact, are not truly constant at all. Everything in physics rests on a set of numbers: the speed of light, the gravitational constant, the charge of the electron, the mass of the proton. These numbers appear in virtually every equation that describes how the universe works. Change any one of them, by even a tiny fraction, and the universe becomes unrecognizable. Atoms do not form, stars do not ignite, chemistry does not work, life does not exist. These numbers are called fundamental constants. And the deepest assumption in all of physics, an assumption so foundational that most scientists never even think to question it, is that these constants are the same everywhere in the universe, and have been the same at every moment since the beginning of time. Among the fundamental constants, one plays a particularly important role in cosmology. It is called the fine structure constant. It is a dimensionless number, meaning it has no units. Its value is approximately 1 divided by 137, and it governs the strength of the electromagnetic force. Because the fine structure constant determines how atoms interact with light, it leaves a fingerprint on every spectrum ever measured. When light from a distant galaxy or quasar passes through intervening clouds of gas, the atoms in those clouds absorb specific wavelengths. The pattern of absorption lines is determined in part by the fine structure constant. If the constant had a different value when that light was absorbed billions of years ago in a galaxy far away, the absorption lines would shift slightly from their expected positions. In the early 2000s, a team led by John Webb at the University of New South Wales analysed absorption spectra from distant quasars. They found hints that the fine structure constant might have been slightly different in the past, slightly smaller. The variation was tiny, less than 1 part in 100,000, but it was statistically significant. The result was immediately controversial. Other teams found conflicting results. Some confirmed the variation, others found no evidence of it. The debate continued for over 2 decades. Then something even stranger emerged. When Webb's team combined data from telescopes in the northern and southern hemispheres, they found that the variation was not uniform. It was directional. The fine structure constant appeared to be slightly larger in one direction of the sky and slightly smaller in the opposite direction. A dipole pattern, as if the universe had a preferred axis along which the laws of physics varied. A truly universal constant should not vary with direction. If it does, the implications are staggering. The universe would not be isotropic at the deepest level. The laws of physics would depend on where you are and which direction you are looking. The James Webb Space Telescope has the spectroscopic precision to test these earlier hints with unprecedented sensitivity. Its near-infrared spectrograph can measure absorption lines in distant quasars with far greater accuracy than any previous instrument. Early results have not yet confirmed or refuted the variation, but the telescope is actively targeting this question. If it detects a variation in the fine structure constant at the level previously suggested, it would be one of the most consequential measurements in the history of physics. Now consider what it would mean if these constants were different in the early universe. Every prediction we have made about the first galaxies, the first stars, the cosmic microwave background, and the evolution of cosmic structure assumes that the laws of physics were the same then as they are now. The chemical reactions that govern star formation, the nuclear processes that built heavy elements inside stellar cores, the atomic physics that determined how the primordial plasma cooled and released the cosmic microwave background. All of these depended on the fundamental constants having their current values. If the fine structure constant was even slightly different in the early universe, our predictions for the early universe would be systematically off, not because the model is structurally flawed, but because one of its deepest assumptions is incorrect. Let us take full inventory of what we actually know about the universe. Ordinary matter, the protons, neutrons, and electrons that make up everything you have ever seen, touched, tasted, or measured, every star, every planet, every cloud of gas, every molecule in your body, all of it contributes roughly 5% of the universe's total energy budget. 5%, that is everything we understand, everything physics can describe in detail. Dark matter contributes roughly 27%. We know it exists because of its gravitational effects. We can map its distribution. We know it clumps together under gravity. Beyond that, we are largely in the dark. Decades of experiments designed to detect dark matter particles directly have found nothing. The Large Hadron Collider at CERN has searched for dark matter candidates in the debris of high-energy proton collisions. Nothing. Underground detectors shielded by miles of rock, designed to catch the rare interaction between a dark matter particle and an ordinary atom, have recorded no confirmed signal. We have a name. We have a mathematical description. We do not know what it is. Dark energy contributes roughly 68%. We know even less about it than we know about dark matter. We know it is driving the accelerating expansion of the universe. We know it appears to be smoothly distributed through space. We do not know what it is. We do not know why it has the value it does. We do not know if it is a property of space-time itself, or a new form of energy, or something else entirely. Add it up. 95% of everything in the universe is something we cannot see and cannot explain. And here is the compounding problem. Our understanding of the 5%, the ordinary matter, depends heavily on our understanding of the 95%. The way galaxies form depends on dark matter. The rate at which the universe expands depends on dark energy. The predictions of lambda CDM for how galaxies should look at any given epoch depend on getting the dark matter and dark energy parts right. If our mathematical descriptions of dark matter or dark energy are even slightly off, the errors propagate into our predictions for the visible universe. Small errors at the foundation compound into larger errors everywhere above. The James Webb Space Telescope has brought these compounding errors into focus with uncomfortable clarity, and they have done so simultaneously, from multiple independent directions, at different physical scales. That is what makes this moment different from previous challenges to the model. In the past, individual anomalies could be addressed individually, but the telescope has produced a constellation of anomalies spanning different observations, different techniques, different redshifts, and different physical scales. Addressing them one at a time is becoming increasingly difficult when they all seem to point in the same direction. Science is practiced by human beings, and the human dimension of this crisis is visible. One senior cosmologist described the experience not as excitement but as vertigo, like standing on ground you trusted completely and feeling it move beneath your feet. The Lambda CDM model is not just a professional tool for the researchers who have built their careers within it. It is the structure through which many of them have understood reality for 30 or 40 years. The tension is visible at conferences. Presentations of new results are followed by pointed questions from the audience. Comment sections in journal papers carry an edge that was absent a decade ago. Senior researchers who once dismissed alternative ideas are now sitting in the front row at talks about modified gravity and evolving dark energy, listening carefully, taking notes. Junior scientists are finding that proposals exploring heterodox ideas that would have been career risks 5 years ago are now being funded. This is what genuine scientific crisis looks like from the inside. Not a dramatic collapse, not a sudden revolution. A slow, grinding discomfort as the evidence accumulates and the conventional explanations stretch thinner. One idea that has lingered at the edges of cosmology for 4 decades is growing louder. In 1983, Israeli physicist Mordechai Milgram proposed a radical idea. What if there is no dark matter? What if gravity itself works differently than Newton and Einstein described? Specifically, what if at very low accelerations, the kind experienced by stars at the outer edges of galaxies, far from the gravitational center, gravity is slightly stronger than Newtonian physics predicts? Milgram called his framework modified Newtonian dynamics, or MOND. It is a deceptively simple idea. Below a certain acceleration threshold, roughly 1/10,000,000th of a meter per second squared, gravity does not fall off as quickly as Newton's inverse square law predicts. It falls off more slowly. This single modification, with a single new parameter, reproduces the flat rotation curves of galaxies without invoking any dark matter at all. For decades, MOND was ignored by mainstream cosmology. It worked beautifully for individual galaxy rotation curves but struggled to explain the cosmic microwave background, galaxy cluster dynamics, and large-scale structure, all of which seem to require dark matter. Lambda CDM explained all of these things. MOND explained only one. In a contest between a theory that explains everything and a theory that explains one thing very well, the broader theory usually wins. But several of the James Webb Space Telescope's observations have given MOND advocates new ammunition. Small isolated galaxies in the early universe that show more rotational structure than Lambda CDM predicts. Their internal dynamics look more like what MOND would produce. Hybrid models are now being explored. Perhaps dark matter exists, but is less dominant than Lambda CDM assumes. Perhaps modified gravity fills part of the structural role that dark matter was thought to play exclusively. These hybrid approaches were once considered unnecessary complexity. Now they are being taken seriously by researchers at major institutions, published in peer-reviewed journals, and discussed at mainstream conferences. When a scientific model begins to crack, theorists do not sit idle. They build alternatives, and right now, at least 4 serious theoretical frameworks are being developed to explain what the James Webb Space Telescope is showing us. None has been confirmed. Each has strengths and weaknesses. The first framework is the most conservative. It proposes non-standard initial conditions. The inflationary period, the fraction of a second after the Big Bang when the universe expanded faster than light, may not have produced perfectly random density fluctuations. The seeds of galaxy formation may have been distributed in ways that allowed faster growth in some regions, certain areas receiving a head start. This approach keeps most of Lambda CDM intact. The equations remain the same. The ingredients remain the same, only the starting conditions change. But it requires an explanation for why the initial conditions deviated from the predictions of standard inflation, and that explanation is not yet in hand. The second framework introduces new physics in the dark sector. Early dark energy proposes that a distinct form of dark energy existed briefly in the infant universe, before the cosmic microwave background was released. This extra energy would have altered the expansion rate during a critical period, changing the predicted value of the Hubble constant and potentially resolving the Hubble tension. Self-interacting dark matter models propose that dark matter particles have weak interactions with each other beyond gravity, which would change the internal structure of dark matter halos and potentially allow faster galaxy formation. The third framework, motivated directly by the DESI results, is evolving dark energy. If dark energy is not a cosmological constant but a dynamic field that changes with cosmic epoch, the entire history of the universe would need to be recalculated. The rate of structure formation, the ages of the oldest objects, the relationship between the cosmic microwave background and the present-day universe, all would shift. The universe's future would change as well. Instead of relentless acceleration toward an empty frozen heat death, other endings become possible. The fourth framework is the most speculative, theories about what came before the Big Bang. For decades, the question itself was considered meaningless. The Big Bang was the beginning. There was no before. But several serious theoretical proposals now challenge this. Roger Penrose, the Nobel Prize-winning physicist, has proposed conformal cyclic cosmology. In this model, the universe undergoes an infinite series of cycles, each beginning with a Big Bang and ending with a vastly expanded, cooled state that mathematically resembles the conditions of the next Big Bang. Penrose has claimed to find evidence for this in anomalous circular patterns in the cosmic microwave background, patterns he interprets as gravitational signatures of black hole collisions from a previous cycle leaking through into our own. Loop quantum gravity suggests that the Big Bang was actually a big bounce, that the universe contracted from a previous phase, reached a minimum size governed by quantum effects, and then expanded again. In this picture, there is no singularity, no moment of infinite density. The universe has existed for far longer than 13.8 billion years. These ideas are not fringe. They are published in peer-reviewed journals by researchers at leading institutions. They are being taken seriously in a way they were not a decade ago. While physicists debate the large-scale structure of reality, the James Webb Space Telescope has been doing something quieter, something that may ultimately matter more than any cosmological model. It has been sniffing the atmospheres of planets around other stars. In the Orion Nebula, one of the most intensively studied stellar nurseries in the sky, the telescope discovered something unexpected: rogue planets. Planet-sized objects drifting through space without a parent star. Not one or two, dozens of candidates. Some appeared to be traveling in pairs, binary planet systems gravitationally bound to each other, but orbiting nothing. Their existence suggests that planet formation is a more abundant and more varied process than anyone assumed. Planets do not only form in the orderly disks around young stars, they form everywhere. The universe makes planets with a profligacy that borders on extravagance. Then the telescope turned to a planet called WSP-39b, a gas giant orbiting a distant star. In its atmosphere, the telescope achieved a milestone: the first clear detection of carbon dioxide in the atmosphere of a planet outside our solar system. The measurement was precise, the signal was unambiguous, and it demonstrated something crucial. The James Webb Space Telescope can identify specific molecules in the atmospheres of worlds orbiting other stars, worlds trillions of miles away, by analyzing the starlight that filters through their thin gaseous envelopes. When a planet passes in front of its host star, a tiny fraction of the starlight passes through the planet's atmosphere on its way to us. Different molecules absorb different wavelengths. By measuring which wavelengths are absorbed and which pass through, astronomers can determine what the atmosphere is made of: carbon dioxide, methane, water vapor, ammonia, and potentially molecules that have no business being there unless something is producing them. Molecules that on Earth are produced exclusively by living organisms, which brings us to a planet called K2-18b. This world orbits a red dwarf star 124 light-years from Earth. It sits in the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. It is roughly 8.5 times the mass of Earth. It may be a Hycean world, a planet with a hydrogen-rich atmosphere overlying a global ocean. In April of 2025, a team led by Niku Madhusudan at the University of Cambridge reported a detection that sent shockwaves through the scientific community. Using the telescope's mid-infrared instrument, they found evidence of dimethyl sulfide in the atmosphere of K2-18b. Dimethyl sulfide is a molecule that on Earth is produced exclusively by marine microorganisms, primarily phytoplankton. It has no known significant abiotic source. If dimethyl sulfide exists in the atmosphere of another world, the most straightforward explanation is biological. The detection was at 3 sigma statistical significance. That means there is roughly a 99.7% probability that the signal is real. The concentrations were enormous, thousands of times higher than on Earth. Then in July of 2025, a NASA reanalysis of the same data reached a different conclusion. The team argued that the signal attributed to dimethyl sulfide could be explained by red noise, random statistical fluctuations in the data that mimic a real signal. They found insufficient evidence to confirm the detection. The debate is fierce and ongoing. The Cambridge team stands by their analysis. The NASA team stands by theirs. Other groups are conducting independent analyses. Additional observations have been proposed. And this is the point. The controversy itself is the milestone. We are now at a stage in the history of science where we can detect potential biosignatures in the atmospheres of planets orbiting other stars and argue about whether they are real. 10 years ago, this was science fiction. 5 years ago, it was aspirational. Today, it is happening. The instruments exist. The data exist. The debate is between competing interpretations of real observations, not hypothetical scenarios. Now zoom out. Consider the full picture. The universe builds structure faster and more efficiently than anyone predicted. Galaxies form earlier. Stars ignite sooner. Black holes grow more rapidly. Heavy elements appear in quantities that suggest stellar evolution operates at speeds our models did not anticipate. If the universe is more efficient at building complexity than we thought, that efficiency extends to planet formation. More galaxies forming earlier means more generations of stars. More generations of stars means more heavy elements. More heavy elements means more rocky planets. More rocky planets means more potential homes for life. And earlier in cosmic history, either life is common, a natural consequence of a universe that builds complexity with the prodigal efficiency the James Webb Space Telescope has revealed, a process running for billions of years across billions of galaxies in billions of potential locations. Or life is rare, an improbable accident that occurred on one pale blue dot, orbiting an ordinary star in an unremarkable galaxy. And we are alone in a cosmos so vast that the distance between us and the nearest living thing is greater than the space between stars. Either possibility is extraordinary. Either possibility should keep you up at night. The universe has never, not once in the entire history of human investigation, turned out to be smaller than we thought. It has never been simpler. It has never been less interesting. It has never confirmed that we had finally reached the end of questions. Every time we built a better instrument, every time we looked more carefully, every time we measured more precisely, the universe expanded. Not just in physical size, but in complexity, in strangeness, in the depth of its mysteries. Galileo pointed a telescope at Jupiter and found moons. Hubble measured distant galaxies and found the expansion. Penzias and Wilson detected the cosmic microwave background and found the echo of creation. The James Webb Space Telescope looked deeper than any instrument before it and found a universe that refuses to match its own description. None of this means the standard model is wrong in the way that a faulty map is wrong. It means it is incomplete. Newton's laws of motion are not wrong. They are incomplete. They work perfectly in everyday situations, but fail at very high speeds and very strong gravitational fields where Einstein's general relativity takes over. General relativity is not wrong. It is incomplete. It works perfectly at large scales, but breaks down at the quantum level where a theory of quantum gravity is needed. Each framework is a step on a staircase that ascends toward a deeper understanding. Each step, when we reach it, reveals that there is another step above. That is the pattern of science. Careful observations reveal accumulated anomalies. The anomalies resist conventional explanation. Theoretical chaos ensues as competing frameworks vie for dominance. And then eventually, sometimes decades later, a breakthrough emerges that resolves the tension and opens an entirely new vista. Newton revealed the question of what gravity is. Einstein answered that question and revealed the deeper question of how gravity relates to the geometry of space-time. Whatever comes next will answer the questions the James Webb Space Telescope has raised and reveal questions we have not yet thought to ask. We are inside one of these moments right now. The anomalies are accumulating. The theories are competing. The instruments are improving. The extremely large telescope is under construction in the Atacama Desert of Chile. When completed in the late 2020s, its primary mirror will span 130 feet, making it the largest optical telescope ever built. It will be capable of directly imaging the atmospheres of rocky exoplanets, analyzing their chemical composition in detail that the James Webb Space Telescope cannot achieve. If there are biosignatures in the atmospheres of nearby Earth-like worlds, this telescope will be among the first instruments capable of detecting them. The Nancy Grace Roman Space Telescope, NASA's next great space observatory, completed construction in November of 2025 and is on track for launch in the fall of 2026. Its field of view will be 200 times larger than the Hubble Space Telescope's, allowing it to survey billions of galaxies across vast swathes of sky. In its first 5 years of operation, it is expected to discover more than 100,000 exoplanets, map hundreds of millions of stars, and observe billions of galaxies. The sheer volume of data will transform our understanding of cosmic structure, dark energy, and planetary systems in ways we cannot yet fully anticipate. The CMB-S4 project, a ground-based array of telescopes being deployed across the South Pole and the Atacama Desert, will map the cosmic microwave background with 10 times the precision of the Planck satellite. If the anomalies in the oldest light are real, CMB-S4 will confirm them beyond doubt. If they are statistical flukes, it will lay them to rest. Together, these instruments will deliver more data about the fundamental structure of the universe in the next 15 years than the previous century combined. The questions the James Webb Space Telescope has raised will be answered. Not all at once, not neatly. Science does not work that way, but the answers are coming. Right now, 1 million miles from Earth, at a point in space called the second Lagrange point, where the gravitational pulls of the Earth and the Sun balance perfectly, the James Webb Space Telescope is still out there. Its golden mirror, 18 hexagonal segments of beryllium, coated in a layer of gold thinner than a human hair, is still pointed at the sky, still collecting photons, still gathering light that has been traveling for billions of years across an expanding cosmos. Ancient light, light from the first galaxies, light from the first stars, light from an era when the universe was brand new and everything was just beginning. And in that light, the universe is still speaking. It is saying something we have not yet fully understood, something about its origins, something about its structure, something about the laws that govern it and the forces that shape it, and the strange, complex reality of a cosmos that builds black holes inside massive gas cocoons, forms galaxies before the simulations say it can, accelerates its own expansion for reasons no one can yet explain, and scatters the molecular signatures of possible biology across the atmospheres of distant worlds. We are listening, we are watching, we are asking, and the universe, as it always has, is answering with more than we expected, more than we predicted, more than any model we have ever built could contain. If this kind of careful, fact-driven exploration of the cosmos interests you, consider liking this video and subscribing. The universe has never been smaller than we thought, and it never will be. The discoveries accumulating from the James Webb Space Telescope do not represent isolated surprises. They form a coherent pattern, and that pattern has a direction. In every domain, the telescope has probed, from the smallest scales of individual galaxy morphology to the largest scales of cosmic structure. The universe looks more evolved, more organized, more chemically mature, and more structurally complex than it should be at the epochs the telescope is observing. This is not noise. Noise is random. Random errors produce disagreements that point in all directions equally. The disagreements here point in one direction. The universe assembled itself faster than lambda CDM allows. To understand why that single statement carries so much weight, consider what lambda CDM actually predicts in quantitative terms. The model says that galaxy growth is fundamentally limited by the rate at which dark matter halos can assemble, and that rate is governed by gravity, which operates on timescales determined by the density of matter and the expansion rate of space. In the first few 100 million years after the Big Bang, dark matter halos could only reach certain maximum masses. The most massive structures that should have existed at a redshift of 10, corresponding to a time roughly 460 million years after the Big Bang, would be halos containing perhaps 10 to the power of 11 times the mass of the Sun. That is the ceiling. That is what the physics allows. And it is approximately what the Hubble Space Telescope found when it looked at those epochs. The James Webb Space Telescope is finding galaxies at those same redshifts, with stellar masses that imply the dark matter halos. Hosting them were already 10 to 1, 100 times more massive than that ceiling. Some of the galaxies the telescope has confirmed at extreme distances have stellar masses of 10 to the power of 11 solar masses or more. That means their dark matter halos must have been roughly 10 times larger still, around 10 to the power of 12 solar masses, in order to have provided the gravitational well deep enough to assemble that much stellar mass. The model says those halos should not have existed yet. The telescope says they did. There is a version of this problem that existed before the James Webb Space Telescope launched, and it was already considered a minor tension. Simulations consistently underproduced the number of massive galaxies at high redshift when compared with the most sensitive Hubble observations. But the discrepancy was small enough, and the observational uncertainties large enough, that it could be attributed to calibration issues, to uncertainties in how astronomers convert the light they observe into estimates of stellar mass, or to the particular way the simulations handle the complex feedback processes by which black holes and stellar winds regulate star formation in massive galaxies. Those are all real sources of uncertainty. The field was aware of them and was working to quantify them. What the James Webb Space Telescope did was take those uncertainties and reveal that they were nowhere near large, enough to account for what the telescope was finding. The discrepancy was not shrinking as measurements improved. It was growing. The more precisely the telescope could measure galaxy properties, the more galaxies it found that exceeded the predictions. Alison Kirkpatrick at the University of Kansas, one of the researchers who was among the first to analyze the telescope's early deep field data, described her reaction in terms that were candid. "I was having a crisis of faith," she said. "I was like, everything I've ever done is wrong." That response may sound dramatic, but it reflects a genuine scientific situation. The predictions she and her colleagues had been working with for years, predictions they had tested against the best available data and found to be robust, were failing at the first confrontation with sharply improved observations. The galaxy formation community has spent the decades since the 1980s developing increasingly sophisticated models of how galaxies build their stellar populations over time. These models, called semi-analytic models, track the growth of dark matter halos, the cooling and collapse of gas within those halos, the ignition of stars from that gas, and the subsequent feedback processes by which newly formed stars and their associated black holes regulate further star formation. They are not simple. They incorporate hundreds of physical processes across an enormous range of scales, from the nuclear reactions inside individual stars to the clustering of galaxy clusters across hundreds of millions of light years, and they have been remarkably successful. They reproduce the observed properties of local galaxies, the statistical distribution of galaxy masses, colors, and morphologies in the universe today, with impressive fidelity. They correctly predict the relationship between a galaxy's mass and the properties of its central black hole. They match the observed evolution of galaxy properties from redshift of 2, corresponding to about 3 billion years after the Big Bang, to the present. These are not trivial achievements. They represent decades of collaborative work by hundreds of researchers across dozens of institutions. But they are failing at redshift above 5, corresponding to the first billion years of cosmic history. And they are failing in a systematic direction. The real universe is ahead of schedule. Galaxies are more massive, more chemically enriched, more morphologically organized, and more prone to early quenching of their star formation than the models predict. Every single one of those failures points in the same direction. The universe is a faster builder than we thought. The question is why? And the answers being proposed reveal just how deeply the telescope's findings cut. One answer involves the efficiency with which gas converts into stars. In the standard models, this efficiency is regulated by feedback. Supernovae explode inside star-forming regions and drive gas outward, quenching further star formation. Black holes at the centers of galaxies drive powerful jets and winds that heat the surrounding gas and prevent it from cooling and collapsing into new stars. These feedback mechanisms limit the fraction of available gas that ends up in stars. Typical galaxies convert somewhere between 5 and 30% of their available gas into stars over their lifetimes. The rest is driven out by feedback or remains in a hot diffuse halo. Some researchers have proposed that in the early universe, feedback was simply less efficient. The first galaxies may have been able to convert gas into stars with higher efficiency than local galaxies, because the physical conditions in those environments, the densities, the temperatures, The chemical compositions were different. If early galaxies converted 50 or even 60% of their available gas into stars, the stellar masses of those galaxies at early times would be substantially higher than the models predict. This is a plausible idea, and there is some observational support for it. The James Webb Space Telescope has found evidence that star formation rates in some early galaxies were extraordinarily high by local standards, producing stars at rates that would exhaust the available gas supply within only a few 100 million years. But high star formation efficiency alone does not solve the problem. Even if you allow every available atom of gas to be converted into stars with perfect efficiency, you are still limited by how much gas was available in the dark matter halos that existed at those times. And the halos, again, are limited by the physics of gravitational collapse. You cannot bootstrap your way out of the halo mass problem by changing the star formation efficiency inside the halo. The halo has to exist first. A more radical solution involves the nature of the primordial density fluctuations. The seeds of all cosmic structure were planted during the inflationary epoch, when quantum fluctuations in the energy density of the early universe were amplified to cosmological scales by the rapid expansion of space. These fluctuations are what became the temperature variations in the cosmic microwave background and the density variations that eventually collapsed under gravity to form halos and galaxies. In the standard model of inflation, these fluctuations have a particular statistical character, called a nearly scale-invariant power spectrum, meaning that fluctuations of all sizes were generated with roughly equal amplitude. This prediction is confirmed to high precision by the measurements of the cosmic microwave background. But there is room within inflationary models for modifications to this spectrum at small scales, the scales that correspond to the smallest halos and the earliest galaxies. If inflation produced more power at those small scales than the standard model assumes, there would have been more dark matter density fluctuations at the small end, meaning the first halos would have been more numerous and would have formed earlier. This would give the first galaxies a larger reservoir of dark matter scaffolding to build on, and it could explain why galaxies appear to be ahead of schedule. This idea is testable. The James Webb Space Telescope itself is gathering evidence relevant to it. If the number density of galaxies at the highest redshifts exceeds the standard predictions by a factor that increases with redshift, that would be consistent with enhanced small-scale power. And that is broadly what the telescope is finding. The excess of massive early galaxies is larger at higher redshifts than at lower ones, which is exactly the signature you would expect if the initial conditions gave an extra boost to the smallest and earliest structures. But enhanced small-scale power has implications beyond galaxy formation. It would also change the abundance and properties of the first black holes, the timing of reionization, and potentially the statistical properties of the cosmic microwave background at angular scales that current measurements have not yet probed in detail. The CMB-S4 experiment, with its tenfold improvement in sensitivity over the Planck satellite, will be able to constrain the small-scale power spectrum with unprecedented precision. If it detects an enhancement at scales smaller than those currently measured, it would provide strong support for the modified initial conditions hypothesis. If it finds no such enhancement, the explanation will have to lie elsewhere. Another possibility that has gained increasing attention involves the way the James Webb Space Telescope itself measures galaxy masses. Stellar mass estimates in astronomy are never direct. You cannot weigh a galaxy on a scale. You observe its light. From the color, brightness, and spectral properties of that light, you infer the age and mass distribution of its stellar population. And from that, you infer the total stellar mass. This inference involves assumptions about how stars of different masses evolve over time, about the ratio of high mass to low mass stars in a given population, a quantity called the initial mass function, and about how much of the galaxy's light is obscured by dust. In the local universe, these assumptions have been calibrated against detailed observations of individual stars and resolved stellar populations in nearby galaxies. But in the early universe, these calibrations may not apply. If the first galaxies had a stellar initial mass function weighted toward more massive stars, their light per unit stellar mass would be higher than local calibrations predict. That would mean their inferred stellar masses, derived from their observed luminosities using local calibrations, would be overestimated. The galaxies would appear more massive than they actually are. This is a real concern, and it is taken seriously. There are physical reasons to expect the initial mass function to have been different in the early universe. The gas out of which stars formed was hotter because the cosmic microwave background itself was hotter at those early times, with a temperature that scales as 1 plus the redshift. Hotter gas is harder to fragment into small clumps, which means it preferentially produces larger stars. Some theoretical models predict that the first generation of stars was dominated by massive objects, perhaps hundreds or even thousands of times the mass of the Sun. If that is the case, then the stellar mass estimates for early James Webb Space Telescope galaxies could be overestimated by a factor of 2 or 3. That would reduce the discrepancy with lambda CDM significantly, but it would not eliminate it. Even accounting for the most generous uncertainties in mass estimation, the most extreme galaxies the telescope has found at the highest redshifts remain in tension with the standard model predictions. The discrepancy might shrink from a factor of 10 to a factor of 3 or 4, but a factor of 3 or 4 in stellar mass still represents a fundamental challenge to the standard formation scenario. And there is a subtler implication. If the first stars were indeed dominated by massive objects, they would have burned through their fuel extremely quickly, enriching the surrounding gas with heavy elements on timescales of only a few million years. That rapid chemical enrichment could explain the unexpected chemical compositions observed in some early galaxies. It could explain the high nitrogen abundances in MOMS E14. It could explain the presence of heavy elements in galaxies at redshifts where only 1 or 2 generations of stars should have had time to form and die. The initial mass function problem and the chemical enrichment problem may be the same problem viewed from different angles. That interconnectedness is characteristic of this moment in cosmology. The anomalies the James Webb Space Telescope is uncovering are not isolated. They are woven together. Pull on one thread and it connects to another. The impossibly massive early galaxies connect to the unexpectedly rapid chemical enrichment, which connects to the possible modification of the stellar initial mass function, which connects to the little red dots and their direct collapse black hole formation channels, which connect to the early quenching of massive galaxies like GS 9209, which connects back to the overmassive halos that should not have existed. The whole constellation of anomalies is internally consistent. It all points to the same underlying situation. The early universe was running faster than the model allows. This internal consistency is actually one of the reasons the community is taking the anomalies so seriously. If the excesses in galaxy mass were the only problem, it would be easier to dismiss them as measurement artifacts. If the only issue were the chemical enrichment, it could be attributed to an unusual population of stars. But when the same directional signal appears in galaxy masses, chemical abundances, black hole masses, quenching histories, large-scale structure formation rates, and the Hubble tension all simultaneously, it becomes much harder to attribute the discrepancies to independent errors in independent measurements. Either the measurements are all wrong in the same direction for completely unrelated reasons, which is statistically very unlikely, or something in the underlying model is incorrect. The scientific community is now in the process of deciding which of those two possibilities is true, and that decision will unfold over the next decade through the combined results of the James Webb Space Telescope, its successors, and the ground-based observatories being built to complement it. The Vera C. Rubin Observatory in Chile, scheduled to begin its legacy survey of space and time in 2025, will observe tens of billions of galaxies over 10 years, providing statistical samples of cosmic structure at multiple redshifts that will either reinforce or challenge the James Webb Space Telescope's findings. The European Space Agency's Euclid mission, launched in 2023, is mapping the large-scale structure of the universe with a combination of photometric and spectroscopic data across more than 35% of the sky. Its primary science goals include constraining the properties of dark energy and dark matter with a precision that complements and extends the DESI results. By the time Euclid completes its 6-year primary mission, it will have observed billions of galaxies across a range of redshifts that spans most of cosmic history. If dark energy is evolving, Euclid will measure the rate and nature of that evolution with sufficient precision to distinguish between different theoretical models. The Atacama Cosmology Telescope and the South Pole Telescope are already collecting data that will feed into the CMBS-4 analysis. Ground-based radio arrays, including the Square Kilometre Array, currently under construction in South Africa and Australia, will observe the universe at radio wavelengths with a collecting area far exceeding any previous radio telescope. Among its primary science goals is mapping the distribution of neutral hydrogen gas across cosmic time, tracing the large-scale structure of the universe through a different observable than any optical or infrared telescope can access. If the cosmic web has properties inconsistent with lambda CDM predictions, the square kilometer array will detect the discrepancy. The convergence of all these instruments over the next 15 years will produce an amount of data about the fundamental structure of the cosmos that exceeds everything collected in all of astronomical history combined. The statistical power will be sufficient to distinguish between theoretical models at a level of precision that the current generation of instruments cannot approach. The questions the James Webb Space Telescope has raised will be answered. The answer may turn out to be relatively conservative: better simulations, more careful treatment of feedback processes, revised estimates of stellar mass-to-light ratios, and modest modifications to the initial conditions of inflation may be sufficient to bring theory and observation into agreement without requiring any fundamental change to the structure of lambda CDM. This outcome, while anticlimactic from the perspective of dramatic scientific revolution, would represent a genuine achievement. It would mean that the framework of modern cosmology is fundamentally correct, and that the anomalies were pointing toward refinements rather than replacements. Or the answer may turn out to be more radical. The accumulating evidence may force a genuine paradigm shift, the kind that Thomas Kuhn described in his analysis of the structure of scientific revolutions. A recognition that the standard model is not merely incomplete in its details, but incomplete in its foundations, that one or more of its central assumptions, perhaps the nature of dark matter, perhaps the constancy of dark energy, perhaps even the universality of the fundamental constants of physics, need to be replaced with something genuinely different. The historical precedents for both outcomes exist. Sometimes what looks like a fundamental crisis turns out to be a measurement problem that dissolves when better data arrive. The anomalous precession of Mercury's orbit, which Newton's laws could not explain, eventually required general relativity to resolve. But many smaller anomalies in the history of physics turned out to have mundane explanations that left the underlying framework intact. What distinguishes this moment is the coherent directional character of the anomalies, the fact that they span so many independent observations and techniques, and the fact that the instruments revealing them are the most precise in the history of science. Previous anomalies could be dismissed partly on the grounds that the measurements might simply be wrong. The James Webb Space Telescope measures at a level of precision that makes that dismissal increasingly difficult. We are, as several researchers have described it, at an inflection point. The standard model of cosmology has carried us further than any previous framework for understanding the universe. It has told us the age of the cosmos, the geometry of space-time, the composition of everything in existence, the origin of all structure from quantum fluctuations in the first moments after the Big Bang. It has been tested against thousands of observations using dozens of independent techniques and found to be correct in its broad outlines with remarkable consistency. And now, for the first time, a single instrument is finding evidence across multiple domains simultaneously that the broad outlines may need revision. The revision may be small. It may be large. It may involve new particles, new forces, new initial conditions, or new geometry. But it will come from data, not from speculation, not from theoretical preference, from the light of the oldest galaxies, the atmospheres of distant planets, the subtle fluctuations in the oldest light, and the three-dimensional distribution of billions of galaxies across 11 billion years of cosmic history. The universe does not care about our models. It does not arrange itself to be convenient. It is what it is, in its full complexity and strangeness, operating according to rules we are still in the process of understanding. Every instrument we have built to look more carefully has shown us that the rules are stranger and more intricate than the previous generation of instruments revealed. The James Webb Space Telescope is the latest in that lineage, and like every instrument before it, it has shown us that the universe is larger, more complex, and more surprising than we thought. The conversation between humanity and the cosmos is ongoing. Every photon the telescope captures is a word in that conversation. Every spectrum it measures is a sentence. Every confirmed redshift of a distant galaxy is a paragraph in a story that has no final chapter, because the universe itself has no final chapter. only an ever-expanding frontier of things still to understand. We are not at the end of cosmology. We are in the middle of one of its most important chapters. And the next page is being written right now, in the data streaming down from a golden mirror floating in the dark between the Earth and the Sun, 1 million miles from home, pointing outward into the oldest light, listening for what the universe is trying to say. If you want to keep following those answers as they emerge, consider subscribing. The universe has more to say. It always does. There is a quality to scientific crisis that is distinct from ordinary uncertainty. Ordinary uncertainty is comfortable. Every working scientist lives with it daily. You do not know the answer to the question you are investigating, and that is why you are investigating it. The discomfort is familiar. The methods for reducing it are clear. You gather more data, refine your analysis, repeat the measurement with a better instrument. The process is well defined even when the answer is not. Crisis is different. Crisis is the moment when you realize that the question you thought you were asking may not be the right question. When the framework through which you have been interpreting your data, a framework that felt as solid as the ground beneath your feet, begins to shift. You are no longer uncertain about the answer within a reliable framework. You are uncertain about the framework itself. And that uncertainty has a different character. It is deeper. It is harder to resolve. It requires not just better data, but better conceptual tools. New ways of thinking about old problems. The James Webb Space Telescope has produced that kind of crisis in cosmology, not all at once, not through a single dramatic discovery, but through the accumulation of evidence from multiple independent directions, all pointing to the same conclusion, that the most successful mathematical framework in the history of science, the framework that has guided cosmological research for 4 decades and has been confirmed by thousands of independent observations, is missing something important about the first billion years of the universe. The missing something is still unclear. It may be a refinement within the existing framework, a better treatment of the physics of star formation and feedback in the extreme conditions of the early universe, a more sophisticated model of the inflationary initial conditions, a more careful accounting for the effects of dust and chemical composition on how galaxies appear to our instruments. These refinements would not require abandoning lambda CDM. They would require improving it, making it more accurate and more complete in its treatment of the early universe. Or the missing something may be more fundamental, a new component of dark matter with properties we have not yet measured, a dynamic dark energy that has been evolving since the beginning in ways our instruments are only now beginning to detect, a modification of gravity that becomes apparent at the low accelerations characteristic of the outer regions of galaxies and the largest scales of cosmic structure. Or even, in the most radical possibility, a variation in the fundamental constants of physics that altered the rates of atomic and nuclear processes in the early universe and shifted the timing of every event in the history of the cosmos. The James Webb Space Telescope cannot tell us which of these possibilities is correct. It has the power to identify anomalies, to measure the properties of objects at extreme distances with unprecedented precision, and to reveal that something in our standard picture is wrong. Determining what is wrong requires the combination of many instruments, many theoretical frameworks, and many years of careful work. That work is underway. What the telescope has given us, beyond any specific discovery, is a renewed sense of the depth of what remains unknown. At a moment when cosmology was in danger of becoming a discipline of refinement rather than discovery, the James Webb Space Telescope reminded the field that the universe still has fundamental surprises in store. It showed us that the era of precision cosmology, while real in its achievements, was not the end of the story, but merely the end of a chapter. The next chapter is being written in the light of the most distant galaxies ever observed, in the spectra of planetary atmospheres, in the statistical distribution of millions of galaxies across billions of light years, and in the quiet, patient accumulation of photons by a golden mirror in the eternal dark between the worlds. The universe is not what we thought it was, and that, in the end, is the best news in science, because the universe being not what we thought means there is still more to understand. There are still questions deep enough to justify careers, still discoveries surprising enough to break open decades of received wisdom, still phenomena strange enough to require genuinely new ideas to explain. The cosmos has not run out of things to teach us. We have not yet asked all the right questions. And somewhere in the data the James Webb Space Telescope is still collecting, In the spectra of galaxies that formed when the universe was less than 5% of its current age, in the atmospheres of worlds that might harbor the first chemistry of life, in the subtle alignments of temperature fluctuations in the oldest light, the universe is still answering. Whether we are ready for the answers is another question entirely. What we know for certain is this: every human being who has ever looked up at the night sky and wondered what is out there is participating in the oldest collaborative project in the history of our species. The question has been asked for as long as our kind has existed. The tools with which we pursue the answer have evolved, from naked eyes to ground-based telescopes to space observatories floating in the perfect dark between the Earth and the Sun. Each generation of tools has revealed a universe larger and stranger than the previous generation could have imagined, and each generation of revelations has shown that the universe is not merely the backdrop against which human life plays out. It is an active participant in the story, a cosmos that builds its structure in ways that continue to surprise us, that obeys laws we have not yet fully written down, that contains within its history the origins of everything we are and everything we might become. The James Webb Space Telescope is the latest and finest instrument in that history. Its findings are the latest chapter in a conversation between human curiosity and cosmic reality that stretches back to the first human who looked up and wondered. The conversation is not over. It has never been closer to its most interesting passages, and the next words belong to the universe, arriving at the speed of light from distances so vast that the light now reaching that golden mirror left its source before the Earth existed, before the Sun ignited, before the Milky Way had assembled its current form. We are listening, and the universe, as always, has more to say than we expected. The process of science is sometimes described as self-correcting. It is, but the description can be misleading because it implies a smooth and automatic process, as if errors dissolve the moment better data arrive and frameworks adjust painlessly to accommodate new evidence. The reality is far messier. Frameworks resist correction. They resist it for good reasons. A framework that adjusted itself at the first sign of any discrepancy would be useless. Science progresses by taking anomalies seriously but not prematurely. The history of physics is full of anomalies that dissolved when the measurements improved, and full of other anomalies that persisted and grew until they forced genuine revision. The challenge is distinguishing between them in real time before the verdict of history is available. That challenge is what the cosmological community faces right now. The anomalies from the James Webb Space Telescope are real. The measurements are, by any reasonable standard, reliable. The telescope is the most precisely engineered scientific instrument in human history, operating in the thermal stability of deep space, calibrated against decades of preparatory work, cross-checked against ground-based observations and complementary space missions. When it says that a galaxy at a redshift of 14 has a stellar mass of 10 billion solar masses, that measurement has been verified through multiple independent spectroscopic analyses. It is not going to dissolve when better data arrive. Better data will sharpen the measurement, not erase it. The question is whether the measurement represents a failure of the model or a failure of our understanding of the model's predictions. Lambda CDM is a framework, but running that framework to produce specific predictions for galaxy properties at a given redshift requires a set of secondary assumptions about the physics of star formation, stellar feedback, black hole growth, and chemical enrichment. Those secondary assumptions are not derived from first principles. They are calibrated empirically against lower redshift observations and embedded in computer simulations whose finite resolution and incomplete physical recipes introduce systematic uncertainties that are difficult to fully quantify. It is possible, in principle, that improving those secondary assumptions would bring the simulated galaxies into agreement with what the James Webb Space Telescope observes, without requiring any change to the underlying cosmological framework. This is the position of the conservative wing of the cosmological community, and it is not an unreasonable position. The simulations have improved substantially over the past 2 decades. The Eagle simulations, the illustrious TNG simulations, the Fire simulations, the Blue Tide simulations. Each has incorporated more sophisticated physical recipes than its predecessors, and each has improved the match between simulated and observed galaxy populations at lower redshifts. It is plausible that the next generation of simulations, incorporating even more detailed treatments of stellar feedback, black hole growth and chemical evolution, will narrow the gap with the high redshift James Webb Space Telescope observations, but the progressive wing of the community notes that the simulations have been improving for 20 years and the high redshift discrepancy has not been shrinking. It has been growing because the observations have been improving faster than the simulations. Every time the Hubble Space Telescope pushed to slightly higher redshifts with slightly better sensitivity, the observations found more massive galaxies than the latest simulations predicted. The James Webb Space Telescope has not revealed a new discrepancy. It has revealed the same discrepancy at much higher redshifts and much greater statistical significance. That trajectory, the observations consistently ahead of the simulations in the same direction across a range of redshifts, is hard to attribute entirely to improvable simulation recipes. At some point, the question has to be asked whether the simulations are failing not because of their treatment of the secondary physics, but because of the primary cosmological framework they are embedded in. That question is being asked more and more openly in the literature. Papers that would have been considered speculative 5 years ago are now published in high-impact journals and receive serious engagement from the broader community. Proposals for early dark energy are being tested against the cosmic microwave background data with genuine rigor. Modified gravity theories are being applied to the James Webb Space Telescope observations, with the specific goal of testing whether they can explain the galaxy excesses. Warm dark matter models and fuzzy dark matter models, in which dark matter has quantum mechanical properties that alter its behavior at small scales, are being constrained by the telescope's observations of the smallest and highest redshift galaxies. Interacting dark matter models are being tested against the internal structure of the protoclusters the telescope is finding. The breadth of this theoretical activity is itself significant. It reflects a recognition that the standard model, while not yet falsified, is under a level of observational pressure that justifies serious exploration of alternatives. The scientific community is not abandoning lambda CDM. It is doing what science is supposed to do when anomalies accumulate. It is building and testing alternatives, not to replace the standard model prematurely, but to be ready if the anomalies persist and deepen, and the anomalies show no sign of dissolving. The James Webb Space Telescope is scheduled to remain operational until the mid-2030s, assuming its fuel holds out. In that time, it will continue to accumulate observations of the early universe, refining the statistical samples that underlie the galaxy mass measurements, finding and confirming more extreme objects at the highest accessible redshifts, and probing the atmospheres of exoplanets with increasing precision as it builds. Up the transit observations needed to beat down the noise in its spectroscopic measurements. Each year of operation will add to the weight of evidence that the community must reckon with. Each new confirmed galaxy at extreme redshift, each new chemical abundance measurement in an early universe object, each new biosignature candidate in a planetary atmosphere will be another datum in the global picture that the James Webb Space Telescope is painting. A picture that, taken as a whole, describes a universe that is not quite the universe lambda CDM predicted. A universe that is faster at building structure, richer in early chemical complexity, more abundant in planet-forming material, and potentially more hospitable to life than the standard model suggested. Whether that picture will ultimately require a genuinely new cosmological framework or merely a significantly refined version of the existing one, history will judge. But the picture being painted is already more interesting, more surprising, and more scientifically rich than the one the telescope was expected to confirm when it launched in December of 2021. The universe had other plans. It always does. Consider what it means that we can ask these questions at all. A species that evolved on a small rocky planet orbiting an ordinary star in the outer reaches of a spiral galaxy in a universe estimated to contain 2 trillion galaxies, each containing hundreds of billions of stars, has built instruments sensitive enough to measure the color of light emitted by individual galaxies that formed when the universe was less than 300 million years old, has measured the Hubble constant to a precision of a few percent using the intrinsic brightness of pulsating stars and exploding white dwarfs, has detected the molecular composition of the atmosphere of a world 124 light-years away, has mapped the distribution of invisible matter across billions of light-years of space, using nothing but the bending of light by gravity, has identified anomalies in temperature fluctuations of 1 part in 100,000 across the oldest light in existence. This is extraordinary. Not in the sense that the word is often used, as a synonym for impressive. In the literal sense, it goes beyond the ordinary. It goes beyond what evolution optimized our brains to do. Natural selection gave us the cognitive tools to find food, avoid predators, navigate social hierarchies, and survive on an African savanna. It did not optimize us for understanding the expansion history of the universe or the chemical composition of planetary atmospheres across interstellar distances. And yet, through the cumulative inheritance of knowledge across generations, through the development of mathematics and physics and engineering and the scientific method, we have built those capacities. We have extended the reach of our perception to the edge of the observable universe and the beginning of cosmic time. The James Webb Space Telescope represents that extension in its most recent and most powerful form. It is not just an instrument, it is the materialization of centuries of accumulated human understanding. From the principles of optics developed in the 17th century, to the quantum mechanics that governs the behavior of its infrared detectors, to the rocket science that placed it at the second Lagrange point 1,000,000 miles from Earth, to the cryogenic engineering that keeps its mirrors cold enough to detect the faintest infrared signals from the most distant objects in the observable universe. Every photon it captures is a collaboration between the curiosity of ancient stargazers and the technical precision of 21st century science. And those photons, arriving from the edges of space and time, are telling us something we did not fully know before. The universe is stranger than we thought. Its earliest chapter looks different from what our best models predicted. The story of how it began, how it built its first structures, and how those structures grew into the cosmos we inhabit today is not yet fully written. There are chapters still to discover, pages still to be turned, and the telescope is still out there. Golden mirror aligned to the sky, collecting the ancient light, adding word by word to the most important story ever told. Whatever the ultimate answers turn out to be, whatever framework eventually replaces or refines lambda CDM, whatever new physics is eventually needed to account for the galaxies the James Webb Space Telescope has found, and the anomalies it has revealed, one thing can be said with confidence. The universe is not less interesting than we thought. It has never been less interesting. It has never once, in the entire history of human investigation, decided to cooperate with our expectations and confirm that we had finally reached the bottom of things. Instead, every tool that extended our vision revealed more complexity, more structure, more strangeness waiting at the next level of depth. The James Webb Space Telescope is no exception. It is the latest instrument to show us that the universe runs deeper than our models, that the bottom is always further down than we thought, and that the questions worth asking are always exactly the ones we have not yet learned how to answer. That is where we are, not at the end, not even at a clear beginning, somewhere in the middle of the most ambitious and most fundamental investigation in the history of human curiosity, looking out at a universe that is roughly 14 billion years old, across distances that make the imagination falter, with instruments sensitive enough to detect the faintest signals from the earliest times, and finding, with every new observation, that the universe has more to say than we expected. It always has. It always will.